Hi there, welcome back to the breadboard. A few videos ago we were looking at Arduino Uno project starter kit from LEDS, and I showed you using it or an AT-Mega kit how to flash an LED and do a couple of minor things with it. And what I want to do now is show you how to do a little bit more advanced hardware, I guess, more than software, but I will show you a modified program as well, using the Uno R3, but driving external loads, because it's all very well and good driving a single LED directly from one of the pins, but in real life, what does that get you? Not very much. And what you see out and about quite typically is driving large LEDs, maybe 10 watt, 20 watt or more, driving relays, solenoids, heaters for 3D printers, stepper motors, etc., etc. Now, I'm not going to go all the way through that in this video, but what I am going to show you is how to drive some external LEDs using transistors, BJTs, that's bipolar junction transistors, and MOSFETs. You do get a couple of 2N2222 bipolar junction transistors in the kit, as you do a whole bunch of different colored LEDs, and I will be using those in this example. But I also have some 10 watt LEDs hooked up that need a 12 volt power supply to operate, and I'm going to show you how you can also drive those using the Arduino Uno, but of course you can't drive more than about 10 to 20 at max for short periods, but really about 10 milliamps from any of the pins of the Arduino Uno. And if you drive these large LEDs, you need 600 odd milliamps per LED to drive them fully on. Now I have three, but I've also got other resistors in place, which is limiting the current to a little bit more than an amp, or about an amp in total when they're all on. This is just a demonstration, so I'm not too worried about it. But you just need, in this case, you just need to increase the voltage from 12 volts or remove my current sense resistor to increase the brightness of the LEDs. Now, just to clarify, LEDs are current devices. You may see ratings for an LED that says 1.2, 1.3, 1.4 volts. But this is a measured voltage across the LED for a given current flowing through it. And you use resistors in series with the LED to limit that current. Otherwise, you run the risk of damaging them or the device that they're connected to. And the same thing goes for regular diodes and the junctions of BJT transistors. They are behaving the same way, in that once you reach their turn-on voltage, you can't just increase the voltage and expect it to increase with it. It will actually limit that and massively increase the current. So you need to pay attention to current limiting and things like that. So you have been warned, but I really just want to show you how to increase your load driving capabilities using a few simple components that you can get from all of your favorite electronic stores, both online and in your local hardware. Without further ado, let's get going with this. So in the picture you can see here, I have the LEDS Uno R3 right here. It's running a sketch that I'll show you in just a moment that sequences through 5 LEDs. The red one, the white one, the blue one. We've got this yellow one. These are the 3 high-powered LEDs here. They're all wired in parallel right now. I've disconnected the power to those because they're swamping the camera out when they're turning on. And then I have a yellow LED here. Now, what the differences are between each of them is that this yellow LED is sitting here working exactly the same way as I did in the previous video. The red LED is connected to a TO22 that's the package type, MOSFET. We'll go through specs and things in a moment. And the next one is a 2N7000 MOSFET. It's in a TO92 package, a little tiny one here. And it has basically the exact same circuit as the first one. There's 100K feeding to the gate, and there's a 330 ohm resistor feeding through the LED, through the MOSFET to ground. And the supply that we're using here is 5 volts from the Arduino Uno. The blue LED is actually being controlled by the BJT, the bipolar junction transistor. That's the 2N2222 that's included in the kit. Here I have a 1K resistor feeding the base of the transistor, and I still have a 330 ohm in series with the LED through the transistor to ground. The one at the back here, I'm actually using a 1K resistor to feed the gate of this MOSFET. Because MOSFETs are voltage amplifiers, or in this case we're using them as switches, they don't consume any notable current when they are turned on or off through the gate. They do have a slight amount of capacitance, so there's always a very slight spike of current when you first change the gate voltage from one level to another, but outside of that, really there is no current being drawn through them. So the resistors are really there to limit the current surge when you first switch their states. For a bipolar junction transistor, we need to limit the current because it is a current controlled amplifier, and you're putting a current through effectively a diode, which limits at about 700 millivolts. Each diode is usually a little bit different, so you need to put a resistor in series with it to limit how much current will flow through that diode, which is called the base in this case, base emitter junction in this very specific case, to just a few milliamps. I think you can put up to about 20 milliamps through the base of this particular transistor. We'll check the specs in a moment. Anyway, so 1K with the 5 volts output, it's a little bit less than 5, but nominally 5 volt from the Uno, will be enough to drive some small LEDs and maybe a little relay or something like that. Anyway, let's have a look at the schematic that I have got set up for you. Okay, here we go. So what I have here is in the middle here, we have the Arduino Uno. I've just done a very basic diagram, as you can see. And we have the bipolar junction transistor connected to pin 11. Pin 10 is connected to the TO92 base 2N7000 MOSFET, and pin 9 is connected to the power MOSFET that is on the breadboard. That's the TO22 type can. Now we have another MOSFET over on the left side here. That's the one that was on the heatsink in this view, so up here. I don't know if you can see it. Oh, I might use my finger. So that's the MOSFET that's on here. It's on a heatsink with a series sense resistor because I've been doing some projects for DC loads and things like that where I've been passing through as much as 10 amps through one of these. So I wanted a heatsink to keep at least the resistor cool. The MOSFET, when it's in switching mode, doesn't get hot at all, but if you're using it in its linear mode, it can get very hot. Anyway, enough of the linear mode. We're not going to touch that here. So that's basically all of the schematics, except for what we have with the yellow LED in that previous view, which is directly connected to the Uno on pin 5. I don't think I put that on here. I'll just put it in there now. So that's on pin 5, and that has a 330 ohm resistor through the LED to ground. So all of these are basically the same thing. I've just color coded them. As far as the LEDs are concerned, they're all the same. They're just, nominally about 1.5, 2.5 volt drop, depending on the type of LED. And they're driven through a switch, which is either the power MOSFET, the smaller MOSFET, or the bipolar junction transistor, or it's being driven directly from the Uno. Either way, it's all very simple stuff that you can wire up on a breadboard. The power one that I have on the separate, those three 10-watt LEDs, those ones are represented by this diagram up here. I actually haven't put the little arrows on the LED symbols. There we go. These three are in parallel. They've got 2 ohm resistors in series with each LED, so if there are any voltage discrepancies between them, it balances it out with the resistors. Go through the switching MOSFET, and then we have a 1 ohm resistor in the bottom, just so I can easily measure current and things. I have other ones with precision resistors in, but for this example, this is just a standard low tolerance power resistor that's just in here. Anyway, so that's all that we've got wired up, and you can see in the zoomed in view here, it's running through quite fine. Red on, white on, blue on, power on, and then the yellow one on, and then they just go off again. Okay, so you can see the wiring is really simple. I've used a breadboard. All the components just plug into the breadboard and they're connected up. I will make these diagrams and things available as a PDF or something like that so that you can look at them yourself. I'll tidy them up using Visio or something. So what is the sketch that's doing this? All right, let's just switch to that so that you can see. So here is the sketch. It's if you've ever played with the Arduino Uno and the blink sketch, it will look a little bit familiar to you. It's been quite heavily modified, but it's basically a blink sketch designed to blink 5 LEDs. I've defined yellow LED, a big LED, a big FET, the regular FET, and the bipolar junction transistor with their pins, so 5, 6, 9, 10, and 11. And then I've defined a delay time of 1000, which would be 1 second. I've also defined a variable called LED state, because when you do the kind of programming I've done here, it gets very long-winded if I wanted to change the delay time from, say, 1 second to half a second, when you have to change half a dozen or a dozen different variables just to change that evenly across them. So I've defined a placeholder where I can set the delay time. The LED state is set to high, and I'm using a trick in the loop to flip-flop it rather than have another equal number of statements to turn the LEDs back off again. So in the setup, we just basically declare all of the pin modes as outputs, and then in the loop, what we're doing here is, this is the same as the blink sketch loop, but it's just been copied and pasted, made longer, and I've modified the state, from saying whether it's on or off, or true and false, high or low, to just being LED state. So up here we saw that LED state just said high. So the first time through this loop, it'll be digital write, big FET, high, delay the delay time, which was 1000, digital write the FET LED state, then the BJT with the LED state, then the big LEDs, that's the triple set off the board with the LED state, then the little yellow LED with the LED state. And then at the very end of the loop, I've said LED state equals not LED state. So it basically, using the exclamation mark there, is programming for not, which means really invert. So if it was a 1, it becomes a 0. If it's a high, it becomes a low. True becomes false, etc. And it'll flip the other way too on each pass. So the first time through, it'll turn everything on. It'll flip LED state to false or low. Then the second time through, it'll turn them all off again one at a time, and then it'll turn them all on again and off, etc., etc., etc. So this one, when I uploaded it, will do exactly what you're seeing in here. Okay, so I'll let it run through one cycle. I'm going to turn the big power LED on in a moment, as soon as it's off. Okay, so I've powered the big LED on, blue, yellow, blinding. The yellow, and then they're white. They look yellow when they're off, and then it cycles through off again. Right, on, big one, off, big one off, and then the yellow one off. Okay, very simple, very easy to understand, I think, if you're done any of the programming for an Arduino. Now, what if I want to make this pulse width modulation? The reason I picked the pins I have is because every one of these on an Arduino Uno is capable of using what they call pulse width modulation. You'll also see the term being used as an analog output, but on an Arduino Uno and on an Arduino Mega, it actually doesn't have a digital to analog converter, so the output is actually a pulse width modulation. We'll get into that in another video if you like. Just let me know in the comments if you want a description of that. But using it, we can effectively dim any one of these LEDs quite easily. So what I'm going to do is I'm going to modify the program to use PWM instead, and the command for that is, instead of just doing digital write, you do analog write, and then you have to change it can't be LED state anymore. It needs to be, if you're going to change its values, any value between 0 and 255. Now you can interchange the PWM in the case of Arduino code like this between a digital write and an analog write quite freely. In the background, the runtime, when you compile it, will actually look at what you're asking it for, and if it's in digital mode, it will flip the internal hardware to be connected to a timer and turn it into a PWM output. And then if you use digital again, it'll flip it back. This is all hidden from you to allow you to keep the programming easier, and the hardware is abstracted away from the user. You can get to much closer to the hardware if you want to, but that's out of the scope of this video. So let me just stop this. I'll flip the code and then I'll show you what the new code is like. I'll put both examples up available for you for download if you want, but for now anyway, we'll just go with I'll change it, show you it, demonstrate it. Okay, I haven't uploaded the program yet. I've modified it. Let's just have a quick look at what I did. So this is basically almost exactly the same program. We've got the definitions for the LEDs. Oh, let me just save this while I remember. Save as. Analog blink. Save. Right, definition stayed the same. LED state, I've changed it from being a Boolean to a byte. Because we're going to be writing a value between 0 and 255, then a byte is more than adequate to constrain that. LED state, and I've set the value to 0 to start with, so the first time through, all of the LEDs should turn off no matter what they were before. Pin modes, definitions stayed exactly the same. In order to create a proper random number, we use random seed. This is just a simple command, and we just read from an analog input, which these devices do have. We just read from analog 0 and whatever. It's just floating around, whatever that happens to be. It just uses it as a seed for the randomizer. It's not necessary in this program, but it's standard practice to put it there. Our loop in the main loop is exactly the same as it was before. LED state and big fat, etc., etc., etc. Difference is at the end, instead of saying LED state equals not LED state, in other words, invert the state, we're just saying LED state equals random 255, which constrains the random number between 0 and 255. Then it's going to go through the loop again. So theoretically, if this compiles and uploads okay, what we should do is see each loop through. We'll speed this up a little bit too. Let's make it 500 milliseconds. We'll just do that, and that changes all of these. It should run through with a certain level, run through with another level, etc., etc., repeatedly until, well, forever basically, using a random number each pass through. So it could be bright, could be dim, etc. Now you got to remember that I'm not scaling the pulse width modulation output. It's just going 0 to 255. But your eyes are not linear from an intensity perspective. So you may not notice some of the brightness changes, even though the value will be changing as much. Again, beyond the scope of this video, but just take my word for it. If it looks a bit funny between values, that's because your eyes don't respond linearly to values of light. All right, let's just power this up. I'm going to swamp it out a little bit. Let me switch to the other screen. I'm going to compile this and upload it right now. Compiling. You're going to see it stop when it uploads. Right there. Now it's done. There's your first pass through. I think I need a print statement to see what the random generator is doing. So I would have expected to notice some differences right now. So let me just switch back to the program and we'll change it. We'll put in a serial dot begin 115/200 baud rate. Okay, and then in here we'll do serial dot print line, and we'll say LED state. All right, so we'll compile this again. I'm not going to put it back to the other screen yet. Let's just compile and upload this. And we'll turn on the serial monitor. What we should do is see values come up here. So 216. Little embarrassing to say. Made a slight boo-boo, didn't quite finish the program off. That's why none of the values are really changing unless we actually output a 0. As you can see, it's outputting random values here quite happily, but none of the outputs are changing. And the reason for that is because I'm still using digital writes. I'm supposed to use analog writes now instead of digital writes. That will be the main difference to go to analog. So you can see the randomized values are working no problem. We don't have to change the definitions, by the way. These are still just pin modes output. But we need to change these to analog like that. So I'll just quickly change those. By the way, that did actually demonstrate the fact that even if I do a digital write with a value between 0 and 255, the output will actually just be off only when there's a 0. Anything other than 0, it'll be on. Now that we've changed this to analog writes, it should start outputting correctly. So let's just switch back, rerun the program, re-upload the program. That's just compiling now, uploading. Let's turn on our serial monitor. That should be fairly bright. Turn that big LED back on again. You can see that just suddenly increased in brightness. That's a low value. You can see they're all turning quite low there. Now they're going a bit brighter again. Let me speed up the program. So instead of delaying only 500, I'm going to make it 100 milliseconds. So it should run through this 10 times a second. Uploading that now. It'll start flickering. All right, so that's how you do an analog output. Now I'm going to slow this down slightly because as you notice here on the right hand side, this meter is actually connected to the 1 ohm resistor on those power resistors. So if I change this back to 1 second delay, when it goes through and turns those on, we'll be able to get an accurate reading of the current. Just remember that 1 volt reading on the meter here will represent 1 amp going through those power LEDs, well, distributed through 3 of them. So there's 370 milliamps. And that was a value of 122 going out. That's 80 milliamps. That's 95 milliamps. 93. I'm waiting for it to get a bigger value this time. $64. It's about midway, 148. That's 450 milliamps. Of course, when you wait for a large value, you never get one, right? Oh, there's one. 238. There you go, 730 milliamps. That's getting up there, 3/4 of an amp. Anyway, you can see that that all works quite nicely between digital writes, analog writes, with external transistors and driving loads. Now, I'm not going to talk about driving motors or solenoids right now. Suffice to say, you do need an additional diode for protecting the transistors, but that's really it. And we're not dealing with isolated circuits here either. All of these, we've got 12 volts from a power brick driving this big LED, and then everything else is driven from 5 volts to all of these. When you're using an Uno like this to directly drive loads, you do need to have the ground as a common between your external supply for the power. For instance, the ground of my 12 volts for this is connected to the ground of the Arduino Uno that's being powered by the USB lead. All these other ones here, they're all sharing the same ground as the Arduino Uno, and they're all being fed from the 5-volt rail as the Arduino Uno as well. When you're using big ones, you want to keep the power side separate and just have a ground reference pin going out with your signal control wire, just so that you're not introducing spikes back into your Arduino Uno. Or better still, use an opto isolator to drive your power loads. Okay, that's completed the overview of the digital write expanded to external loads using MOSFETs and transistors, etc. Hope you liked that, and if you did, give us a thumbs up. In the second video, to go with this, I'm splitting it into two to keep them around or under 30 minutes each, hopefully. We'll look at data sheets for the components that I've been using, explain a little bit about them, just so that you can understand what parts we're using. A lot of the parts are included in the video. A lot of the parts are included in the Elegoo kit, though, as far as the 2N2222s, the LEDs, the resistors, etc. Other ones you can get from a number of different places. I'll provide some links in the description. And yeah, so anyway, so now head off to part 2 if you want to watch it right away, which makes it a little more exciting when it comes to doing things with your Arduino.